So thanks for inviting me. I'm really glad that Macallan Martin really put this together. I've known Mike and Eric a very long time, probably both since the 80s. Because it seems like most speakers seem to gravitate towards one or the other. In my case, it's Eric that two of us go pretty far back. So I started to try to count how far back. So we've been to 30 computational complexity conferences together. I know this because there are 31 of them, and I missed the one in Porto, and Eric's never missed. He's been the one person to meet all 31 complexity conferences. And probably at least 20 dog stools that we've been to together. And I looked at the very first dog stool in complexity in '92, and there were 6 people from that conference who talked at that dog stool who were here. Eric, myself, Harry, Steve Homer, Neil, and Ken. I don't know where you were, Jack, but yeah. And it's kind of interesting when you hear stories about when Harry met you in Amsterdam, I was there. When you in the lobstool picture, I was there sitting next to you. At your pool party, I didn't see me, but I saw my wife and 2 daughters as babies who are now in college. In India, I was there. We've been together in New Zealand. Let's figure 4 continents. What else did I write? Probably that. It's hard for me to think of the first time we met, but it might have been the '86 complexity number 1 in Berkeley. Eric was the computational complexity chair for 3 years, and then I followed him doing a 6-year gig. I was the editor-in-chief of Transactional Computation for 3 years, and Eric followed me doing a 6-year gig, which, by the way, he just finished 6 great years as ACM. As editor-in-chief, he just stepped down, and so I really want to thank him for taking his journal and making it, make it into a very strong venue. It's hard to think of. I was trying to rack my brain from all these 50 or so different events I've probably been to, and with Eric, trying to think of some embarrassing stories, and it's not so easy. What can I say about Eric? If people know that he's a big dancer, that he can speak at least conversational German. That this is something I even noticed early on, that Eric really has this voice that sounds like it ought to be in radio, and apparently, as Eric was telling us in high school, that's the local radio station owner figured that out too and put him on the radio. And what town was it? Mount Pleasant, Iowa. And also, I'm now at Georgia Tech, and Eric is a Georgia Tech alum, PhD, 1985. So you were there before there was a College of Computing. It started in 1990. I got you an official College of Computing. Shared for your, so you say, okay. The development office will be contacting you soon for donations. So anyway, really, but here's the one, I think, and Eric and I share a lot of common interests. We both work in Kolmogorov complexity, we both worked in reductions, both worked in the isomorphism problem, we've worked on printable sets. We've done a lot of common stuff and not a single joint paper, which is very strange, really, considering how close I am to Eric. So someday we gotta change that.
You've reviewed all of each other's grants.
So technically, I think since we've been one each other's editor-in-chief, I think for the last 9 years, we couldn't review each other's grants. At least I haven't reviewed any of yours.
It never came up.
Okay. So, yeah, we just conflicted in other ways. So, okay, so I'll move on with the talk. I was trying to think of what of what to talk about when it came to Eric, and Kolmogorov complexity really, randomness really seems to be a theme that's sort of been part of my career for a very long time, and is certainly very important. And so I want to talk about some results that were very well connected with Eric, and a little bit connected with me. That kind of connects complexity and randomness. So it's kind of a viewpoint of like when you flip a coin. I mean, what random thing is happening? Nothing random is happening. It's just that we can't. Some messy computation is happening while the coin flips, and you can't predict whether it's going to be heads or tails. So for all practical purposes, it's random. And I think this is really what, in some sense, to me, this is what randomness really is. It's not a magical process like quantum, does God throw dice? It's really a complex operation that we don't know what the answer to, so it appears magically like it's random to us. So there's a really close connection between complexity and randomness, and there's loads and loads of results to kind of show that out. But I want to look at one particular sequence of results, and that's what is the complexity of the random strings? And what does that even mean? What does it mean for a string to be random? I'm going to kind of go through this initial part at least a little bit quickly. Hopefully a lot of you are familiar with Kolmogorov complexity. But I'm not going to use that much deep stuff from Kolmogorov complexity. Basically the idea is you measure the randomness of the information in a string by the size of the smallest program that generates that string. So, for example, you have a program of a billion zeros. You can write a program that says, from I equals 1 to a billion, print 0, and so if you have n zeros, you need about log n bits to describe that program. But if the program is just complete, stuff you get from a truly random source, if such a thing exists, then really the shortest way you can describe the program is to say print that string, basically, and then those kinds of things are what we call random. So formally, you kind of fix some universal Turing machine. I'm not going to, for the results I need, the exact definitions aren't going to be that important for the kind of results I'm going to talk about in this talk. But you say X is random if you can't shrink, if the smallest program that generates X is at least the length of X itself. How many random strings are there? Well, if you allow me well, first of all, there's a counting argument that shows such things exist. There just aren't enough smaller programs to generate all the strings of length n. If you allow me a little bit of slack, then almost every string is really close to random. So 99.9% of the strings, it's just a counting argument, or at least x minus 10. I'm just going to stick with this definition. So let R be the set of random strings with this definition. And it's a bit of a messy argument, but you can show that a constant fraction, where the constant depends on a universal Turing machine, of the strings are random. And that's basically the only fact that I need. And that, these are actually programs that you can describe. So one sort of first fact that you kind of see when you start doing this work is that the random strings, and this is even kind of surprising when you first say it, kind of how does this work? So random strings, you can solve the halting problem. So I give you an index of a Turing machine, and you have access to an oracle of strings which are somewhat random. You can use them to determine whether or not your machine halts. And I find, why should random information give you the halting problem? Well, it's not quite random information, it's a set of random strings, and that's what you take advantage of. So I'll just give you a sketch of the proof. Let's let P, many of you have probably seen this, but let's let P be a problem, a program, a program of length n, and you want to know whether or not P halts. And what you do is you can't generate random strings, but you can generate non-random strings by trying all the small programs, all the programs less than length n, or in this case, I'm going to look at strings of length 2n, and I'm going to look at all the strings there that are not random. And I want to start generating the non-random strings. And I'm gonna do that until I've generated all the non-random strings. And here's where I use whenever I have access to I have access to R as an oracle because I'm trying to, I want to show R is as hard as the halting problem. So with that, I know what the random strings of length 2n are, so I can know when I've generated all the non-random strings of length 2n. And see how much time that takes? That number is t. T is going to be huge. It's roughly busy beaver of 2n, so it's going to be a really big number. But we're not trying to be. I'm just being computable here. Yeah. And then my claim is that if p halts at all, it will halt within t steps. And then once that's true, then the test is easy. You take your program p, you run it for t steps that you figured out in the last step. And if it halts sometime, you say it halts. If it doesn't halt in t steps, you know it's never going to halt. So you say don't halt, and you've solved the halting problem. But why? Why is this statement true? Well, suppose it isn't true. So suppose you have a p of length n that halts in more than t steps. So it halts in some number of s steps that's greater than t. So first what I'm going to do is let x be the lexicographically least random string of length 2n. So there's a set of random strings of length 2n. X is the smallest one. Now in this little sub-argument, I'm not going to assume I have access to R. Okay, so I don't know what x is, but I'm going to give a short description of x. That's the goal. So I run this p, which halts in some number of steps s, and by assumption, it's going to be more than t steps. And so I generate all the non-random strings of length 2n in s steps. But since s is greater than t, I've generated all the non-random strings. And then x is the least remaining string. So I've described x by p, which has n bits, and maybe log n extra information. Maybe even a constant extra information would be enough. And that's a contradiction from the fact that x was a random string and cannot have a description shorter than 2n. And that's the proof that given the random strings, you can actually solve the halting problem. Yeah. This kind of reduction that I give you is something. It's actually called a weak truth table reduction. It's a truth table reduction in this. A truth table reduction in the computability world means that there's a bound to how large the questions I ask are. So it's bounded by I'm only asking questions of length 2n to the oracle. So I'm not. So there's a bound on it, but the point of a truth table reduction requires that I halt even if I get the wrong answers. And that's not the case here. If I get the wrong answers, I'll try to be generating strings, forever, not finding them. So this is actually a weak truth table. A weak truth table reduction is where there is a bound, but you're only guaranteed a halt if you actually had the correct oracle. So that's the difference between a weak truth table and a truth table. And this turns out to be an interesting case, as far as I know, the only interesting natural case of a weak truth table reduction. Oh wait, I missed something here. So there are a lot of neat other things you can ask about R. And so I want to talk about a whole bunch of results about the power of R. So it's kind of a spoiler slide because this is all the things I'm going to talk about. And I should say there are stronger versions of some of these things, for different kinds of notions of randomness, sometimes for time bounds. But I just want to focus on this particular R because I just love all these results. One is that you can actually get rid of the weakness, is that you can just do it with the truth table reduction. One is that you don't need the full power of computability. You just need you know a polynomial time with a little bit of advice. The p space you can compute in polynomial time with a random oracle, and these last two results are due to a wonderful paper by Alan Berman, Kautsky, Van Melkebeek, and Runenberger from 2006. NEXP, you can get all of NEXP. If you use NP to the R, you can get all of NEXP, which is, it's basically an exponential jump by adding random strings. That's kind of cool. So that's Allender, Berman, and Kautsky. I'm getting your name right.
Stick with Cookie.
Cookie, fine. Cookie. A relatively new result that XDNP is in PDNP of the random oracle by Hirakawa, and my kind of small contribution to the world, BPP is in P to the random string. This shouldn't surprise you that BPP is in P to the like you're using randomness to get randomness, but it turns out there's an issue here. When it was non-adaptive queries, and I'll explain why that's an actual. It's not trivial, but it can be done. Okay, so this first theorem is actually probably the most complicated of all the proofs. I'm not going to do it here. It was a beautiful proof by Kummer. I tried to teach it once, it's not constructive. I mean, it creates a series of reductions, one of which will be a truth table reduction. So it's not even particularly constructive, but it does show that the truth table reduction must exist. Yeah.
So, is there a reason to believe that the first result without the slash poly?
You mean the second one?
Oh, I'm sorry.
Yeah.
The second one. Yeah. Which
that
would
you can get away with.
That's an open question.
Yeah.
Yeah. I mean, there's not a reason to believe that it's not true. Or.
I'd be surprised. So, I don't know how much of this I want to hijack, but Kummer's result gives a particular type of truth table reduction that's just, you come up with a list and you say, are any one of these things random? And if that's the type of truth table, if that's the type of reduction you're giving, then the running time has to depend on the universal machine. You can always pick a universal machine that makes the running time Ackermann of Ackermann and really, really awful. And that's the only type of truth table reduction that we know about. But we still don't know how to disprove the fact, it might be polytime.
It seems unlikely. Or it could actually depend. In some of these cases, it could depend on the actual choice of the universal machine. So, as far as none of these results, as I believe, are known to be tight. Except, in certain ways, there's you can look at them in tightness, but there's a lot more that's unknown here than known. So I want to do this proof because I think it's to me this is it's a cool application of pseudorandom generators. Using Kolmogorov and Kolmogorov connecting it with Kolmogorov complexity. In particular, we're going to look just at the basic Nielsen-Richardson generator, the original one from it's 94 was a journal version. It's actually 89, a hardness versus randomness paper. So their main result was that if exp is not approximated by, I'm going to give a series of results, trading off hardness and randomness, and they normally talked about it. So basically they showed it not for generic A, but for exp. If you can't approximate x by polynomial size circuits, then you have a sub-exponential time pseudorandom generator that goes from n to the epsilon bits to n bits for any epsilon. But they don't need x, but they just need any a. If you can access it as an oracle, if you take any a that can't be approximated by polynomial size circuits, then you can use that a to create a generator. And not only that, the generator only queries a's on strings of length n to the epsilon. So the picture would be like this. And in fact, what it really does is G just takes the bits of A intersects sigma n to the epsilon, and it takes the seed and uses the seed to take a subset of bits and applies the hard. Anyway, I won't go into exactly how the generator works, but it takes 2 to the n, it takes a into section n the epsilon here, it takes the seed here, it generates some string here. So it looks a little bit like an extractor. That's not too surprising. Actually, Luca Trevisan showed a really neat duality between extractors and pseudorandom generators, relativized versions of pseudorandom generators. And I tried to actually find an extractor result that I could use for this, but I couldn't find the one with the right parameters. But the interesting part about hardness, the way we're using hardness for randomness, and this is, I think, the really coolest idea, was to look at the contrapositive. It says that if I have a problem that's hard to approximate, then I can fool and get generated fools linear size circuits. Well, if my generator fails to fool linear size circuits, then the function has to be easy to approximate. It's just the contrapositive. And then on top of that, so contrapositive. Wait, what did I do? Oops, I did things in the wrong order. Sorry. First I want to notice that you can actually relativize this theorem. So if you can stick B here, and you can if you allow B gates, you can allow P to the B / poly here, and the theorem goes pretty much right through. And then you can look at the contrapositive. So if you fail to, if G fails to fool some circuit with B gates of size n, then A is approximated by P to the B poly language. So what are we going to use for A and B? Well, the obvious thing seems to be is you should use B is the random strains, because you want to show that A is computable. You want halting problem to be computable in P to the R / poly, so you want that conclusion to read that the halting problem is computable in P to the R / poly. So the first clear thing to try to do is use, well, let's let B equals R and A equals halt. Now that doesn't work because it's only going to give you the halt as approximable by P poly language. And then it depends on how you define halt. And you define halt the wrong way, you could just always say no and maybe approximate it. So how do you get around that problem? There's lots of ways. Basically, just take some reasonable error correcting code for halt, and then if you can approximate, if you get an algorithm that gives you the correct answers for most of an error correcting code, then you can use the error correction to get everything else correct. That's the beauty of an error correcting code. And now here's a critical point. It was so critical that actually last week I had to email Eric because I was confused by it. But he has set me straight. The strains of, if you look at all the strains of length m of halts, you can describe not just one of them, you can describe all of them. All the 2 to the m, all the exponential number of strains of length, all the 2 to the m possible strains of halt, you can determine with only m bits of information. What are those m bits? Well, there's a couple ways to do it. One is look at the last program that halts. Because if I tell you the code for the last program that halts, well, then you can wait until that last one, and you can enumerate all the halting programs until that last one halts, and then you know you got them all. Or you can encode the number of halt problems that halt, and then you can just count them until you got them all. Either way, you really only need m bits to describe all of the 2 to the m possibility bits for halting. So halt, oddly enough, is not a random set. Halt is compressible. And that's a critical point. And since halt is just an error correcting code for halt, fancy halt is an error correcting code for halt, you don't need any. You need the same number of bits, just like a few extra bits to describe the error correcting process, but it's computable. Okay, so we're going to use Now here's the key here. The key is just is this point here. Is so in here I put in halt, the fancy halt on sigma n to the epsilon, and here's my seed. And now I want to claim is the output of this generator can never be an R. Why? Because I only need n to the epsilon bits. Remember, I only need n to the epsilon bits to describe this whole sequence. There's only n to the epsilon bits here. So that's 2 times n to the epsilon. Some code for the generator, maybe log n bits to describe n. Nevertheless, that's all going to sum up to something less than n. And so any output has a description of size roughly n to the epsilon, so it's not random. So the output cannot be an R. So if I have access to an oracle for R, it's really easy to create a circuit that this generator is not full. Just check whether the output's an R. Because if I have something that's outputted from the generator, I'll always miss R. That probability will be 0. If I choose something randomly, then there's a constant fraction chance that I'm in R, and that's enough. So that's a constant difference, and that's enough to violate the pseudo-randomness of G. And so it must be the case that fancy halt can be approximated in P to the R / poly, and then you just use error correction. Well, error correction to show that halt is computable in P to the R / poly. So hopefully I got all that correct. A little bit of hand waviness, but that's the basic idea. And it's kind of really cool that you can get all the way to halt this way in P to the R with polynomial device. So yeah, I'm going to go through some of these other theorems, but to me I just find that amazing. It's just the halting problem. That's like hard. And it codes a lot of information. It's harder than the exponential time hierarchy, which is not a small circuits whatsoever. and yet we can solve all those things, anything computable, and even a halt. I mean, it's just dumb. Oh, okay. If you get rid of the advice, things drop a bit, but still, I think some really neat results. So, P space in P to the R. How does this go? So I'm going to be a little more sketchy as we move on. I don't even see when does my. I want to keep track of that.
375.
What?
45 each.
345? 245. I have what?
20 minutes.
I have 20 minutes, okay. So the nice thing about this talk is if I can I'll just skip something if I don't finish in time. Okay. So P space and BPP to the R. This is a little trickier, so I'm kind of not going to go through it in gory detail, but let me give a rough idea. It follows from this Impagliazzo-Wigderson 2000. There are 2 Impagliazzo-Wigderson papers that really deal with pseudo-randomness. This is the 2001 version, and the main result was that if exp is different than BPP, then there's a sub-exponential simulation of exp that's correct in most input strings. So this is kind of a neat de-randomization result. I don't know if I'm glad or not that Avi had to leave early, so he can correct me on anything I'm going to say. So what does this say? This really says, I mean, if BPP fails to get X completely, then you can do some de-randomization. There's a deterministic sub-exponential time simulation of X that's correct in most input strings. It's kind of cool. Well, I'm not really going to use a contrapositive directly, but the idea, the proof works by contradiction. You assume that there is a sub-exponential simulation of, you assume that, so we start with X not equal to BPP. That means that X is non-P-poly. You get some you get some collapses already, and then but in the end, the chunk comes from this statement, which is that if you have a language that's both downward and random self-reducible, so downward reducible means you can take an input, and if you had an oracle for smaller inputs, you can solve it. Random self-reducible means you query a bunch of random strings from some distribution independently of the input, from the input, and you can determine what the input is. So the permanent is your kind of standard example of something that's downward self-reducible and random self-reducible, and that was the key to showing that the permanent had interactive proof systems way back when. So for L downward and random self-reducible, Pagels-Wigderson gives a generator that's based on this language that if the generator fails to actually be a generator, then L is computable in BPP. It actually gives a probabilistic way to generate circuits for BPP. Now, again, we can use, this relativizes, I'm not going to go through all the details, but basically, again, this relativizes to R. Again, using kind of a basic setup, you can show that the output is not going to be random. R lets you violate the generator. The generator fails. So so basically, we can show relative to R that any L that's random downward and random self-reducible, that it's downward and random self-reducible is going to be computable in BPP relative to the random sets. Now, every downward self-reducible set has to be in p-space, and in fact, there are complete. That's tricky to show, but there are complete sets that are downward and random self-reducible p-space. So that puts p-space in BPP to the R. Now, how do I get from BPP to the R to P to the R? And now, how do we get all these papers and work together, but they never intersect? I don't know. It's like we had to, Eric and I really had to work hard not to actually write any papers together. So this is work I did with Harry and with Alon Newman and Nikolai Vereshchagin. So, first of all, this sounds like it should be trivial. So if I have access to all these random strings, let me just find a random string a little bit larger than a BPP and use that random string, plug it into the BPP algorithm, and that's basically what we do. But the problem is that if you start on if your input is not random, then it could be it's not clear at all how you actually find a random string. After all, because if you just queried a random string right away, well, that would be a very short description, and so it wouldn't be random. So it's if you find it, it's not there. But the trick is, in fact, we have random strings not just for length n or whatever, but for all the smaller lengths. And it's easy to find a random string length log n. You just query all the strings length log n. You have polynomial time. You find a random. And then what we do is we just do a trick to, once we have a string of length I, to find a string of length I plus 1 that's random. And then we kind of work our way up until we get long enough random strings, and then we plug it in. And then it's basically just using expanded graphs. And in fact, they're extremely simple expanded graph constructions. So basically, you take your random string of length I, throw on a 0, and now it's very close, still close to random for length n I plus 1. If it's random, you're done. If R0 is random, just take it. But if R0 is not random, it still has to have Kolmogorov complexity, basically n minus a constant. So basically what we do is just consider expanded graph with the nodes of size 2 to the n, but in some compressed format. Take the string R0, look at the radius of length order log n, I forget exactly what the parameters are, search all the polynomial strings there, and then by by the expander property, it's not too hard to argue that one of those strings has to actually be a random string. And it's not obvious. If you didn't have R itself, you wouldn't be able to find one, which is why you can't actually use this to create a real random string. But we do have access to R. So we just check all these strings, find out which one is random, and now we have a random string of length I plus 1, and then we repeat the process until we get a random string long enough to plug into our BPP algorithm. So that's how we get BPP in P to the R, and then therefore we have P space in P to the R. So, and now if you allow NP, it's neat how these results changed over time. Originally it was P space in NP to the R using interactive proofs, but then you came up with this, well, one neat way to get P space there. And now next in NP to the R, which again, the first time I saw this proof was pretty messy, but now it seems really simple. Just look at the PCP theorem, the version where you have an exponential size PCP for NEXP. This is a Bave for now Lund, just to ring my own bell for a second. Now this is the exponentially large PCP, and it's computable. You can't even figure it out in X, but you can compute it in X to the NP. In X to the NP, you can do some binary searches and find a PCP if it exists to show that the language exists. So you understand what everyone's seen PCPs? This is the verifier is polynomial time. This is an exponential size PCP. It gets to query things randomly, and that convinces the verifier, if it's in a language, there'll exist a PCP that convinces the verifier. And you can get all of NEXP this way. Well, X to the NP is in P to the halt, because X to the NP is computable. So that's in P to the R / poly. So that means that there's a polynomial size circuit that describes, with access to the random oracle, but that's okay, this describes this PCP. So in NP, I guess that circuit, and then I simulate the verifier asking random questions by having the verifier pick large R's. Now with NPDR, it's easy. You just non-deterministically guess large random strings. You don't have to go through this whole process. They could if you wanted to, but them more slowly. And then use the verifier pulls random strings, pulls randomness from the oracle to therefore check that the PCP is valid. And that's how you get NEXP in NP to the R. Just do this manually. XDM, so if you allow XDMP, you get P to NPDR. This is a result. I don't know this proof because, and I got this all from looking at Eric's papers and Eric cites personal communication or something, but I meant to get it from you before this talk, but I failed. So let me talk about this last one, which seems a little too. So now I want to get BPP and P to the R, which again sounds like, well, didn't we already do that? We did this process of pulling up the strings longer and longer. But here I only want to ask non-adaptive queries. So which means that I have to ask all my queries ahead of time. And if I do that, it's impossible for me to define any long random strings in R. But what we do is we show that, but I can find strings of length log n non-adaptively. I just query them all, and what we do in this paper show that has high circuit complexity. If it has high circuit complexity, you can plug it into the other Impagliazzo-Wigderson generator. And they used to use both of them in this talk, and that'll de-randomize BPP. So why does it have high circuit complexity? Well, let's suppose the set of random strings has small circuit complexity. And I'm not going to define how large and small. You have to get the parameters just right to make this work. But here's the rough idea. So for each circuit C, so let's just look at all the possible circuits. Look at all the possible circuits. For each circuit, let's let R sub E C be the set of strings that C claims are random. What does that mean? That means that C is going to give you a set, and maybe the set is a set of random strings, and for some C it is. We don't know which C it is, but we know some C it is. Okay. Now we know that the set of random strings is the least constant fraction of all the strings. So if R sub C gives you a set which is very small, then throw it away, because we know that's wrong. So just throw it away. So all you have left are large sets. And now the point is, if I have a lot of large sets, I can find a relatively small set. Like if I have an exponential number, I'm just giving an example. If I have an exponential number of sets, each of which are a constant fraction of strings, if I pick a polynomial number of strings at random, then with high probability I'll intersect every set. So this uses a tighter version of that, but that's the basic idea. You can have an exponential number of sets. If they're all large and I pick a polynomial number of strings, they'll intersect every set just by kind of standard probability arguments. So there's a small number of strings that intersects every large RC. And not only that, we've just managed to compute it without knowing anything other than maybe what n is. So I showed you how to come up with it randomly, but you can brute force it. I'm trying to be computable here. You can brute force it and find out, find that small set of strings that intersects every large RC. Now, if one of those RCs is actually correct, then that RC only has random strings. This set that intersects it, therefore, the small set of strings that intersects it must have a random string in it. But if that's the case, then in your small set, every element of your small set has relatively low Kolmogorov complexity. You just give the index, what's the 12th element of the set, for instance. That's relatively small description. And so you can't have a small number of strings that contains a random string, and that's a contradiction. So that's a contradiction. It's impossible for there to be, for a set of random strings to have small circuit complexity, and you can really, if you push this carefully, you show that, in fact, it doesn't have sub-exponential size circuit complexity, so therefore it's good enough that we can use it to de-randomize BPP, and that's how we de-random. So that's how we get BPP and P to the R, non-adaptively even. So I think that times well. This is about the end of my talk. I just want to kind of mention, mentioned this a little bit earlier, but we don't know whether any of these are tight. There's some results on certain kinds of Kolmogorov complexity. Maybe if you're dependent on the ordering, that gets you some tightness here. Eric's got a huge number. You should just read Eric's papers. They're just wonderful.
Yeah,
Lots.
That was going to be my question. How does this depend on the definition that you said?
Yeah, it could depend on the universal. We don't know. It depends on the universal quantifiers. Are there other kinds of results like this? Particularly, there seems to be a gap with PDR and non-adaptive queries. Can you get all of P-space and PDR non-adaptive queries? Is that open?
It's still open, although it's looking unlikely. So Shuichi Hirahara has some results on a slight tweak of that puts it in P-poly intersect sigma 2, which is getting really close to BPP.
Oh, well, that's good. So there's even results that are still coming out on this stuff. So, to me, it's just this whole series of results, particularly this, well, I wouldn't say the first one, this second one, this Halton PDR/poly, and how that whole thing played out. And how every time I go to a conference, Eric would so excitedly meet me and say, look what we proved now. Can you improve this? We can be co-authors. And of course I can't. And then of course Eric does improve it. Next time we see him at conference, we got it down to got P-space and PDR. And, yeah. And we used your paper with Harry. And I'm like, damn, I thought I could have been a co-author. So, but yeah, no, it's exciting to see how. I mean, fun towers. It's exciting to see how this played out. So it's kind of a neat thing here, and there's loads of other just neat connections. And there's just a tiny fraction of really neat connections between randomness and hardness, and I think it's just a beautiful duality that I think really needs even more exploring. So, thanks very much. So I see questions. You can call.
So I have one question. Has anyone tried to quantify, either concretely or axiomatically, the amount of redundancy in Kolmogorov complexity, the effect of multiple programs giving the same output?
Well, it comes up in the universal distributions.
Yeah, that's true. That kind of.
I mean, you could show things like there are an exponential. There's a constant fraction of strings that are non-random, and there are constant fraction of strings that are random, but all these things depend on the universal Turing machine, and so it gets a little tricky.
Just an observation based on teaching out of CIPSR for the last 10 years. He has a little section on Kolmogorov complexity, and he has an exercise at the back, which the exercise in there, which is to show that the testing randomness is unsolvable. And he has there's another exercise there which says show that the function that takes something and gives its Kolmogorov complexity is unsolvable. And it turns out that that second problem, which sounds more complicated, is actually easier because you can use the Richard paradox. The Richard paradox is what is the least, you define the least English number not describable in fewer than 42 English words, and that number can't exist. But if it were computable, then the least function which is describable in fewer words than it has, is a contradiction. So, but that doesn't give the result you gave, which is the constructive reduction, which is why this is really neat.
Okay. Yeah, there's a lot of neat tricks. I mean, R, for example, is a wonderful example. It's like the simplest example of a Mune set, right? So, I mean, any infinite computable subset of R is finite, and its complement is computably enumerable. So, there's all these messy constructions, such things, and R just does it. Right. So there's all sorts of neat properties of R that I really haven't talked about. So, yeah, I love this stuff. Still doing it, So, okay. Any other questions?
Thank you.
Thanks.